Welcome to another open learning session where I'm going to catch up with deep learning. This video series is about me self-studying the mathematics. It is not a tutorial or where I'm going to teach you. It's actually just me recording how I will read this textbook. This is called The Mathematics of Machine Learning. It's an open MIT published book. The link is in the description. I will encourage you to just join me and study that book by yourself. And I hope that from time to time it's valuable to just see how I'm going to do one of those chapters and struggle and maybe sometimes when you don't understand the chapter and you just see me doing it, it helps. So last time we did the chapter 2.5 and today we are talking about basis and rank. In a vector space V, we are particularly interested in a set of vectors that possesses the property that any vector V can be obtained by a linear combination of vectors in A, like in a set of A. These vectors are special vectors. In the following, we will characterize them. Okay, so basically we have a bunch of special vectors. Yeah, we have a bunch of special vectors and we can use linear combination to basically construct many more vectors. And that set of many more vectors is the vector space. Well, actually, it's just the set. It's also what we learned. The vector space also needs an operator, or two operators. But in any case, you have two sets, V and A, and you can construct a much bigger set A by the special vectors V. Generating set and basis. Definition. Generating set and span. Consider a vector space V and a set A, where we have A as a subset of the vectors. Yeah, I don't know. Cursive V. If every vector can be expressed as a linear combination of x 1 to k, A is called a generating set of V. The set of all linear combinations of vectors in A is called the span of A. If A spans the vector space V, we write V equals the span of A, or V equals the span of the vectors x1 to xk. Generating sets are sets of vectors that span vector subspaces. For example, every vector can be represented as a linear combination of vectors in a generating set. Now we will be more specific and characterize the smallest generating set that spans a vector or a subspace, a vector space. Okay, so what I'm understanding is we have a thing called a span, and that span is basically a set of all things you can construct with the vectors in V. Sorry, the vectors in A. So you have A, which is a set, like there are many vectors, and then you have a set V. Basically, it is a vector set, and not a vector space, and then we call that a span. I don't know why. you can span out maybe. I don't know. Does it make sense? But at least it makes sense that you can construct a vector space from this vector or from this set of vectors, and then we call it basically a span of A. Definition 2.14 basis. Consider a vector space V and A is a subset of the vector set V. A generating set A of V is called minimal. If there exists no smaller set A hat, which is let me double check. What is that? Must be a subset. Not sure what the first symbol is. I think it means not a subset. But usually the crossing line is bigger. But in that case, it would still make sense, because what we are saying is that there is no subset of A which generates the span V. Every linear independent generating set of V is minimal and is called a basis of V. So once we have found a minimal set which generates the vector space V, we call that minimal set basis. That makes sense. Okay, so let's go on. Let V be a vector space and be a subspace which is not empty. Then the following statements are equivalent. Oh, okay, no, I read this wrong. Again, let V be a vector space and be a subset of the set V. Then the following statements are equivalent. So this one is not a subspace, it's a subset. Just got confused with the V because this is a emphasized V. Oh man, I will just call those set V and set B. No, that's wrong. Or is it? Can we call it set V and then vector space V? Or vector set V? I don't know. So thing is that we should know that that is a vector space and that is a vector set. Maybe that's how I call them from now on. Okay, so the vector set B is a basis of the vector space. The vector set B is a minimal generating set. The vector set B is a maximal linearly independent set of vectors in vector space V. Adding any other vector to this set will make it linearly dependent. Yes, that makes sense. But I do not understand maximal linearly independent. Is there like some kind of a degree how linearly independent you can be? I don't think so. You're either linearly independent or linearly dependent. I think this term maximal is wrong. Okay, let's move on. Every vector x of the vector space is a linear combination of vectors from the vector set B, and every linear combination is unique. So what they're saying is you have a vector x, and that vector x is the sum, or basically it's a linear combination of the vector B. So you have k dimensions, then you have basically not dimensions, or can you say it like you have k different vectors in B. Then you take each of those vectors in B, the small b in this case, 1 to k, and then you put them next to each other, and then you give each of those a different scalar. Then you combine them, and then you have a new vector x. Now you take the same bunch of vectors, and then you give them a different scalar. So in the first case, you give them the scalar which all belongs to lambda, and then the other one is, what is this actually? Let me double check. It is C. I never learned these Greek letters. Okay, so you construct them. So basically what they're saying on this equation is, let's have a vector x. You construct them basically using lambda, which is a vector, like 1 to k, and you have C. But if you have the same resulting vector x, well, that can only be if lambda and C is the same. There's no other way. Oh yeah, that's what they're saying here. It is the same. I was confused. I was like, huh? If they're the same, then lambda and C has to be the same, but I couldn't find it. Yeah, they have to be the same, and it makes sense. If you just take, let's just try to use a minimal example. You have basis vector 1, 0 and 0, 1, yeah? B1 and B2. So let's say we want to have the vector 2, 2. That is our x. Now we can construct it by saying, maybe let's say not 2, 2, but 2 and 3. It's always easy to use different prime numbers, because then you will see where the difference is. So we need to multiply b1 with 2, and we add 3 times b2, right? Makes sense. Then you will this will result in a vector 2, 3, x. Let's call it x1. Now, is there an x1? Can we conclude that there's or can we find a way to go and have x1 by finding a different number, c1, from b times b1 plus c2, b2, so that c1 is not 2, c2 is not 3. Well, it's not possible. Like, you can reduce the problem by saying, okay, let's just take a look at that one. Just the first one. We want to find what is 2 if we multiply c1 with b1, and we know that b1 is 1. Well, only 2 will solve this. Therefore, this equation makes sense. So C and lambda cannot be the same. Or every vector is a linear combination is unique. Yeah, that makes sense. Okay, example 2.16. In R3, the canonical standard basis is, that 2.73, and we can say a different base is that one. What they mean is, for example, let's just go in 2 dimensions. This could be one basis, but you could also have a basis like this. That also makes sense. The only thing which is important is that you have a right angle here. So you can basically say that you have a point. So you have a point, and you can say that, yes, if I move this point along this axis, then only one number changes and not the other one. So that's what they are saying, that if it's independent. In this case, I'm looking at the blue basis. If I look at the black basis, then this would be this way, or the other axis, one of those. But maybe we can discuss this later. So, okay, you have these two different bases, and both bases are generating the set R3, or basically the vector set, if you want, if you add the plus and the scalar operator together, then you can have a vector space. And here you have a different set, vector set A, and they're saying A is linearly independent but not a generating set of R4. Oh no, okay, this is a complete different set. For instance, the vector 1, 0, 0, 0 cannot be obtained by a linear combination of elements in A. Okay, so what they're saying is, just because you have different vectors, like in A, you cannot conclude that you can generate all like the vector space R4. And they show it by an example saying there's a vector which you cannot obtain. So the span of A, of the vector set A, is not the vector space R4. Remark, every vector space V possesses a basis B. The preceding examples show that there can be many bases of a vector space V. For example, there is no unique basis. However, all bases possesses the same number of elements, the basis vectors. So the number of elements is the same. What they mean with elements, I think the number what you have in the base in the base set. So for example, in R3 you need to have 3 different vectors no matter what. The vectors itself, they can be different, but they cannot be like 4, so or just 2. That makes sense because if you have less, then you cannot express every dimension. And if you have more, then they are linearly dependent because one of those is a linear combination of those other 3. Yeah. So you have redundancy, and a basis has to be minimal. Okay, let's move on. We only consider finite dimensional vector space V. Okay, good. In this case, the dimension of V is the number. The dimension of V is the number of basis vectors of V. Yeah, okay. I used already the term dimension. And we write dim V. So, and it makes sense, if U is a subspace of V, then the dimension has to be less or equal, because the subset can also be the set itself of V. And yeah, of course, it can be, and it is the same if V and U is the same. Intuitively, the dimension of the vector space can be thought of as the number of independent directions in the vector space. Yes. Remark, the dimension of a vector space is not necessarily the number of elements in the vector. Okay, that's what what? The dimensions of the vector space is not necessarily the number of elements in the vector. for instance, the vector space V, which is built by the span of the vector 0, 1, is one-dimensional, although the spaces vector possesses two elements. Oh yeah, that makes sense. That makes sense. Okay, so what do they mean here is, let's say you have two vectors, one here and one here. Now you can ask yourself, what vectors could you construct by scaling those? And you could, even though this is not a right angle, let's say it's 30 degrees, you could still construct basically a whole plane. So you can reach every point in this plane, right? So basically you want to reach that point here, then you would go here first, scaling this one, and then you would scale that one. Or maybe not exactly like that, more like this, so that you still have this 30-degree thing. Or you go and scale them down, this one here, and then you will scale it here. And you still have 30 degrees. No, not here, but I think here. Here's 30 degrees. Okay, so this is the usual case, but you could find a solution, or not a solution, but like well, a case where you start with a single vector. In this case, we have 0, 1. Now, what vector space can you construct? You can make it bigger in this way, you can make it bigger in this way, you can make it smaller, you can make it smaller. But all you can do is basically you're stuck on this line. But you can reach every single point on this line. So you still can construct infinite many vectors. It's just that the vector space is one-dimensional. But here we have a two-dimensional vector. Yeah. And the reason is because the null is basically not scalable. But it does not really, no, it's not really null, because you could say, oh, what if we have 0.5 and 0.5 vector, right? And if we just do it classically, then you will have something like that. And you still are stuck. Let's just put a coordinate system here. Right, here have x1 and x2. And you still are stuck on this line, the green one. This is your vector space. Okay, that makes sense. That all makes sense. I'm really happy that I'm not confused here. Okay, let's move on. Remark: a basis of a subspace U, which is constructed by the span of x1 to xm, which is a subset of Rn, can be found by executing the following steps. Write the spanning vectors as columns of the matrix A. Okay. Determine the row echelon form of A. Okay. The following vectors associated with the pivot columns are a basis of U. Yeah, that makes sense. It's quite, yeah, okay. So basically write it down as a matrix, get a step form, and every pivot is a basis, every pivot column. You can, not every column must be a pivot, right? That means that, let's say you end up with 10 columns and only 3 of those are pivots, then you will have a 3-dimensional vector space. Okay, here's an example. They start with, okay, for a vector space, for a vector subspace U from R5 spanned by the vectors x1 to x4. Okay, you have 4 5-dimensional vectors. We are interested in finding out which vector are a basis of for U. For this, we need to check whether x1 to x4 are linearly independent. Therefore, we have to solve this equation, which will result in a null vector. So they write it down as a matrix, and then they do the transformation. Now, from this transformation, we can see we have a pivot column here, a pivot column here, and a pivot column here. Since the pivot columns indicate which set of vectors is linearly independent, we see from the row echelon form that x1, 2, and 4 are linearly independent. Because this equation can only be solved when those lambdas are 0. Therefore, x1, 2, and 4 is a basis of U. Okay, so yeah, that makes sense. So made a mistake before explaining something. The dimensions are not the number of bases, the number of vectors in the base set. It's the number of elements what you have in the vector space, of one vector in the vector space. Let me think again. What we have here is a dimension. The definition is the dimension of the vector space V is the number of basis vectors of V. The number of vectors. Yeah, of course, the number of vectors, of basis vectors. Yeah, it makes sense. Of course, yeah. Because here in that case, we have only one vector, therefore we have only one dimension. Here in that example, we don't know which one is the basis vector. We just have 4 vectors. But it spans a 5-dimensional, like each vector is 5-dimensional. Each vector is 5-dimensional. You have 4 vectors. And then you will find that only 3 of those are basis vectors for that subspace. Okay, so how can we understand this? Let's say we have some kind of a 5-dimensional space, and within that 5-dimensional space we have a subspace. Okay, so let's zoom out, or zoom in basically. Here is our subspace. Now we have 4 points, and these 4 points are used to span this yellow space. Yeah, we construct, we say U equals the span of X. Yeah, for x1 to x4. So just by having the 4 vectors, we can actually compute or define U. Now, just because yellow lives within blue does not mean that yellow has to be 5-dimensional as well. It can be 3-dimensional. Like a plane can exist in a space and a line can exist in a plane. So when they're asking what are the bases, what they want is, let's do it in red. So what we want is we want to find the basis of U. So which one of those 4 dots or points can we do we must have? And then in the end, we will have like, we say, okay, this is important, and that's important. Yeah, this is like our three vectors. And then we say we can still construct the yellow box, but we only need those red points. The fourth one is not needed. That's what they're saying. So we have 5 dimensions for each of those. Well, we have a 5-dimensional vector, but the subspace is actually just 3-dimensional. That's something we need to understand. Like within that subspace, okay, let's say you can move within that subspace just in 3 different directions, like independently. That's I don't know. It makes sense in my head, but it's quite hard to explain. Well, you just have to remember that if you have a plane like here, you still can have a line, and within that line you can have like a dot, and then you can move that dot up and down. But if you say the subspace is just a line, then there's really only one direction the red dot can move if it's constrained to that subspace. But like in general, we can say that red dot has 2 dimensions because it has like from like the bigger context. You have a number x1 and a number x2. And let's say number x1 is I don't know, 2, and x2 is in this case 3, and here it's 4, and here it's 5, here's 6. And if you want to move, so even though you can only move x in one direction or in one dimension, it has two numbers. And that's the same as in this whole case here. Each of those vectors in green, they have 5 numbers, but the subspace U is just 3-dimensional. And you have 3 degrees of freedom. Okay. I think I will just leave it like that. Let's remove that part here at least. Maybe we can do this in red as well. But this was quite an interesting topic. So what I have learned here is that I learned that the subspace can be less than the space or the superspace. And just because you have a 5-dimensional, or not dimensional, but a vector of 5 numbers, does not mean it has to be 5-dimensional, because the dimensionality actually is the number of bases you have to span the vector space. So you can have 2 vectors, base vectors, which span a vector space, but each of those 2 base vectors can be like a vector of 10 elements. That does not mean that the space they span is also 10-dimensional. It is 2-dimensional. It just you just need 10 numbers. Okay, let's continue. 2.62. Rank. The number of linearly independent columns of a matrix A equals the number of linearly independent rows and is called the rank of A and is denoted Rk of A. Okay, so we have a matrix. We have independent columns, and also that number has to match the linearly independent rows. The rank of a matrix has some important properties. So the RK, the rank of A is the same as the rank of the transpose matrix. What they're saying is the column rank equals the row rank. The columns of A span a subspace U with the dimension of U is equal to the rank of A. Later we will call this subspace the image or range. A basis of U can be found by applying Gaussian elimination, the Gaussian elimination of A to identify the pivot columns. Okay, wait, so we're checking the columns of A. All right, so we're talking about a subspace of Rm. The matrix is M times N. So let's say we have 2 times 3, a matrix like that, something like this, right? Then we have 3 columns. Then we want a subspace. So we will say U is a subspace of R2. Okay. Then just because we have a subspace, we don't know the dimension of U. Because U can be 2-dimensional, 1-dimensional, or 0-dimensional. So if we calculate the rank of A, then we know that the dimension of U has to be exactly the rank of A. So maybe it's 2, maybe it's 1, maybe it's 0. But before calculating the rank, we don't know. We don't know this number. Okay, let's continue. The rows of A span a subspace W, basically with the same thing, just in this case A transpose. For all A of a square matrix, it holds that A is regular, invertible. It means that the square matrix has an inverse if and only if the rank of A equals n. Okay, I'm just marking some important things. Okay, next one. For A in Mn, for all vectors in Rm, like all vectors which is at the shape of the column, it holds that the linear equation Rx equals B can be solved if and only if the rank of A equals the rank of AB, where AB denotes the augmented system. Okay, we can basically use the rank to find out if the linear equation can be solved. That's quite helpful. For A and Rmn, the subspace of solutions for Ax equals null vector possesses dimension n. N is the number of rows. No, the number of columns. Sorry. So that the number of columns minus the rank of A. Okay, so what they're saying is we want to find a solution for this equation Ax equals 0. So we will find basically all different x versions. And then you can say, all right, let's say you find some kind of equation with like this lambda stuff. Yeah, like x, you find an x with this lambda inside. And then you want to know, okay, we're not talking about one vector, we're talking about like many vectors, which can solve that. Now you want to know for that subspace what dimensions they have. And it cannot be like in a case of a rank of 0, it has the same dimension as A. Sorry, it has the same dimension as the number of columns. But for every rank we have in the matrix, it has one dimension less. Later we will call this subspace the kernel or the null space. A matrix A has full rank if its ranks equals the largest possible rank for a matrix of the same dimension. That means that the rank of a full rank matrix is the lesser of the number of rows and columns. What they mean is the rank of A equals the lesser of m or n. A matrix is said to be rank deficient if it does not have full rank. Okay, so we have full rank and we have rank deficient. So it's either full rank or it's rank deficient, all right? But we said that a rank is the number of linearly independent columns or rows. Okay, I think I'm not understanding the last part. Let's do the example first. All right, so we start with a matrix. A has 2 linearly independent rows and columns, so that rank is 2. Okay, I can see this one independent and one independent. Let's write down a transpose. I'm not sure here. I mean, we can subtract R1 here, and we can subtract R2. Well, if we do that, then we will have something like that. And I guess still then we will have two independent columns, because we are talking about a transpose, then it will flip and become like rows. But this is what I would say. That's why we have a rank 2. But they have to be the same. So here we're saying that they have to be the same. Okay, so what do we have here? This is just a new matrix. They say we use Gaussian elimination to determine that rank. Yeah, I guess what they're looking for is the staircase thing. So 1 and 2. Okay, yeah, still it has a rank of 2. Well, that's it, right? I'm not really getting the last part, but this is just a bunch of definitions. Yeah, in the end, I need to write down all these definitions and I need to memorize them. Like, no matter what, how much you can understand it, you first need to like start somewhere. I think most of it I understood, but still, I need to memorize those. But that's it. That's it for this chapter. In the next video, we will talk about linear mappings. So thank you for watching and see you next time.